Welcome to this lecture on beta and gamma functions. Imagine you are building a house and need to cut hundreds of wooden planks to a very specific, complicated shape. You could measure and cut each one from scratch, which takes forever. Or you could make a reusable stencil. In calculus, the beta and gamma functions are exactly like these mathematical stencils. They are pre-solved templates for incredibly difficult integrals, and today we will learn how to use them. Now that we understand the idea of mathematical stencils, let us look at our first tool, the gamma function. Why does this function matter? In mathematics, we easily understand factorials for whole numbers, like 4 factorial or 5 factorial. But what if you need the factorial of a fraction or a decimal? The gamma function provides the exact mathematical answer to that question. It is an improper integral, meaning its upper limit stretches endlessly to infinity. Essentially, it is a mathematical machine that takes a number, plugs it into a specific infinite integral, and spits out a result that behaves exactly like a factorial. This concept leads us directly to the formal definition of the gamma function. The formula you see here is the engine behind this stencil. We denote it with the Greek capital letter gamma. Inside the integral, n is our positive input number. The variable x is what we are integrating over, and e is Euler's number. Conceptually, the exponential term ensures that as x gets very large, the entire expression shrinks down to zero. This prevents the infinite area from blowing up to infinity. As your input n increases, the peak of the curve shifts to the right, and the total area under the curve grows extremely fast. Having seen the definition, we must now understand its most important feature, its recursive nature. Why is recursion so crucial here? Because calculating infinite integrals from scratch every time is exactly what we want to avoid. The recursive property means that the gamma function of a larger number can be expressed in terms of a smaller number, stepping down exactly like a traditional factorial. This is the secret bridge that connects a continuous smooth integral curve to the discrete step-by-step multiplication we know from basic arithmetic. This recursive concept is captured in a beautifully simple formula. Gamma of n plus 1 equals n times gamma of n. This tells us that to find the value for a given input, we can just multiply the previous input by its gamma value. Because of this step-down behavior, if our input n is a whole number, the gamma function simplifies perfectly into a standard factorial. Specifically, gamma of n equals n minus 1 factorial. If n increases, the resulting factorial grows exponentially larger. This simple rule is our ultimate shortcut for avoiding tedious calculus. Before we prove why this recursive rule works, let us see it in action with a concrete example. We want to find the exact numerical value of gamma of 5. Because 5 is a whole positive integer, we do not need to evaluate the complex infinite integral. We simply use our factorial shortcut. We substitute 5 into our formula, which tells us to subtract 1, giving us 4 factorial. We then expand 4 factorial into basic arithmetic. 4 times 3 times 2 times 1. This gives us a final answer of 24. Physically, this means the infinite area under our complex exponential curve is exactly 24 square units. Now that we have calculated a value, let us look at what this function actually represents visually. On this graph, the horizontal axis represents our input n, and the vertical axis represents the output of the gamma function. Notice the specific points plotted. At an input of 3, the output is 2. At 4, it is 6. And at 5, as we just calculated, it shoots up to 24. The solid blue line is the gamma function itself. It is a smooth, continuous curve that perfectly threads through all these discrete factorial points. It visually proves how the function bridges the gap between whole numbers and continuous mathematics. So we have seen the formula, used it, and graphed it. Now let us understand where this recursive property actually comes from. By proving it. We are setting out to prove that gamma of n plus 1 equals n times gamma of n. We start by writing the standard integral definition, but we replace the input n with n plus 1. The plus 1 and minus 1 in the exponent cancel out, leaving us with x to the power of n. To solve this, we use integration by parts, which undoes the product rule of derivatives. We strategically choose u as the polynomial part, x to the power of n, because taking its derivative will reduce its power. Continuing with our proof, we now need to find the missing pieces for our integration by parts formula. We take the derivative of u, which brings the exponent n down to the front and reduces the power by 1, giving us n times x to the power of n minus 1. Next, we integrate dv. The integral of e to the negative x is simply negative e to the negative x. Now we have all 4 puzzle pieces. We substitute them into the integration by parts framework, giving us a boundary evaluation term from 0 to infinity minus a new integral. This new integral looks messy, but notice that the two negative signs will cancel each other out. Bringing this proof to its conclusion, let us evaluate the boundary term first. When we plug in infinity, the exponential decay completely overpowers the polynomial growth, driving the value to 0. When we plug in 0, the x term makes it 0. So that entire first bracket vanishes. We pull the constant n out to the front of the remaining integral. If you look closely at the integral that is left behind, it is the exact original definition of the gamma function for the input n. Therefore, we can replace that entire integral with the symbol gamma of n. This gives us our final result, proving exactly why the gamma function steps down like a factorial. Now that we have mastered the gamma function, let us introduce its partner, the beta function. Why do we need another function? While the gamma function handles infinite bounds, the beta function is a specialized calculator for finite, bounded areas. It takes 2 inputs instead of 1, and it is defined as a definite integral strictly between 0 and 1. Think of it as a tool specifically designed to find the area under curves that bulge in the middle and taper off at the ends. As you change the 2 inputs, the shape of the bulge shifts, and the beta function instantly tells you the new area. This brings us to the mathematical definition of the beta function. We denote it with the capital letter B. Inside the integral, m and n are our 2 positive inputs. The integral runs from 0 to 1. The term 1 minus x is crucial here. It creates a natural boundary that forces the function to drop to 0 as x approaches 1. Conceptually, the balance between the exponents m minus 1 and n minus 1 determines whether the curve leans to the left or the right. If you increase m, the bulge shifts right. If you increase n, it shifts left. Having defined the beta function, a beautiful and highly useful feature is that it is symmetric. This means swapping the order of the 2 inputs does not change the final output. Let us prove this property step by step. We start by writing down the standard definition of the beta function. To prove the symmetry, we will use a technique called integration by substitution. This is like changing the currency you are using to make the math easier to handle. We introduce a new variable y and set x equal to 1 minus y. Geometrically, this substitution essentially flips the graph horizontally. Continuing our proof, since we changed the variable, we must also change the differential and the limits of integration. Taking the derivative of x equals 1 minus y gives us dx equals negative dy. Next, we check the limits. When x is at its lower limit of 0, y must be 1. When x is at its upper limit of 1, y must be 0. We substitute all of these new pieces back into our original integral. Notice that our limits of integration are now upside down, going from 1 down to 0, and we have a negative dy at the end. Now we simplify the messy algebra to reach our final result. The expression 1 minus 1 minus y simplifies beautifully to just y. Furthermore, we use the negative sign from the dy to flip the limits of integration back to the standard order of 0 to 1. This is a standard rule of calculus. Finally, we rearrange the terms to put y first. This new expression perfectly matches our original beta function definition, except the positions of m and n have been swapped. This gives the final result, proving the symmetry. Physically, this means the total area is identical whether the shape leans left or right. So we have proven that symmetry holds for the beta function. This brings us to the most powerful concept in this topic, the beta-gamma relationship. Why is this so important? Because evaluating the beta integral directly is still very difficult. However, the true power of these functions unlocks when we connect them together. The beta function can be written entirely in terms of gamma functions. This is an incredible shortcut. Instead of solving the complex integral for the beta function, we can just look up or calculate 3 simple gamma values and divide them, turning advanced calculus into basic arithmetic. Let us look at the formula that makes this shortcut possible. On the left, we have the beta function of m and n. On the right side, we have a fraction made entirely of gamma functions. The numerator is the product of the gamma functions of the individual inputs, m and n. The denominator is the gamma function of the sum of those inputs. Conceptually, this formula is a bridge. If you increase either m or n, the gamma values in the numerator grow, but the sum in the denominator grows even faster, which perfectly calculates the shrinking area of the beta curve. Before we move on, let us see this relationship with a concrete example. We are asked to evaluate the definite integral of x squared times 1 minus x cubed from 0 to 1. We could expand the polynomial and integrate term by term, but that is tedious. Instead, we recognize that this perfectly matches the stencil of the beta function. To use our shortcut, we must identify our m and n values. By comparing our specific problem to the general template, we set up 2 simple equations. The exponent on x gives us m minus 1 equals 2, and the other gives n minus 1 equals 3. Continuing with our example, we solve these basic algebraic equations instantly. Adding 1 to both sides gives us m equals 3 and n equals 4. We have successfully identified our parameters. This means our complicated integral is exactly equal to the beta function evaluated at 3 and 4. Now, we apply the powerful relationship formula we just learned. We place our m and n values into the fraction. The numerator becomes gamma of 3 times gamma of 4, and the denominator becomes the gamma function of their sum, which is gamma of 7. We have transformed the integral into gamma functions. To find the final numerical answer, we evaluate these 3 distinct gamma functions. Since all inputs are whole integers, we use our factorial shortcut rule, subtracting 1 from each input. Gamma of 3 becomes 2 factorial, gamma of 4 becomes 3 factorial, and gamma of 7 becomes 6 factorial. We expand these into their full multiplication sequences. Notice that the sequence 3 times 2 times 1 appears in both the top and bottom, so we cancel them out. Multiplying the remaining numbers gives 2 over 120, which reduces to 1 over 60. Physically, this means the exact area under our polynomial curve is 1/60th of a square unit. We have covered the full topic, so let us review the most important ideas. First, remember that the gamma and beta functions are powerful mathematical tools that act as pre-solved templates for difficult integrals. The gamma function extends the concept of factorials to all numbers, allowing us to calculate continuous curves. The beta function handles complex, bounded curves and acts as a specialized calculator for specific shapes. Finally, by linking the two together, we can bypass tedious calculators entirely, transforming impossible-looking integrals into manageable, everyday arithmetic. You now have the tools to solve these complex problems with confidence.